I'll do the first one slow, I2O5. I want to figure out the oxidation state. So actually, we can do the first one really fast. Oxidation state for oxygen. Careful. -2. Right off the bat, I don't have to do anything else. Because it's not in its elemental state anywhere in the reaction, it's always going to be a -2. Okay. For iodine as a reactant, there's 2 iodines. I don't know the oxidation state, plus the number of oxygens, 5 times its oxidation state, -2, which equals the overall charge in that unit, which is 0. 2x minus 10 equals 0. X equals +5. Okay. I've now done half of the questions that I need to solve for. Okay. In this process, you have to go through and do all of this. Whoops, that was not the right eraser. You have to determine those oxidation states. And you have to get those relatively fast, because the next question is, what happened? What happened to the iodine? To go from a +5 to a 0. It had to gain 5 electrons. So we could reveal that information. What happened to the oxygen? Nothing happened. What happened to the carbon? It lost electrons. So what we now have is a gain and a loss of electrons happening within our reaction. So what we can now do is subcategorize this and define each of those elemental changes according to either a reduction or an oxidation. We define the loss of electrons as oxidation. We define the gain of electrons as reduction. So to get to an answer, you have to determine all your oxidation states and then match them according to the correct phrase. Because what I might ask in this question is, what species was oxidized? Okay. The species that was oxidized is the one that lost electrons. Which one lost electrons? Oh, yeah, you're right. Carbon lost electrons. Okay. If you don't go through and solve all that work above, you're doing it in your head. Don't get me wrong, you can do it in your head correctly, probably most of the time. Okay. But if your most of the time is 80%, are you happy with a B? Okay. If you are, have at it. Okay. For those of you that aren't at an 80% on getting it consistently correct, you need to be writing out all the work. Eventually what will happen is you will get tired, we've said this already, you'll get tired of writing out the work and you'll start to get irritated at me because you're like, why is he making me write out all the work? And it will get stuck in your brain and you will do awesome on the test. That's what I'm looking for. Just don't get too angry at me. Okay. How do we... The slight moans after that were not pleasant. How do we memorize that loss of electrons is oxidation? The one that sticks in my head, personally, is Leo says Gur. Leo is a lion. Leo the lion says Gur, because a lion is a big cat, and most cats... Gur. There we go. Leo says Gur. Okay. You will notice if you ask me any question about what's happening, is it oxidation or reduction, almost always under my breath you'll see me go, Leo's Gur. Leo, loss, electron, oh no, that means it was reduction. Okay? I don't keep it straight in my head. It's very easy to get confused. Okay? Which means you have to come up with some device to make sure it's stuck in your head. I will say, for some reason at this campus, I am the only one that likes Leo says Gur. In fact, I've talked to other chemistry faculty that are like, oh, Leo says Gur, that's kind of cool. I wonder why I haven't heard that before. Because your teachers weren't as cool. The other one that gets popped out that you'll see in this throughout your coursework here is oxidation is loss of electrons, reduction is gain of electrons. Same idea, except it comes up with oil rig. I'm too much of a green hippie to stick with oil rigs. Some people get it. Okay, listen. Drum roll, thank you. Sorry, before we do that, questions on this? Okay, I know it's a lot. You're being asked to do a lot of this. As far as the questions that show up, maybe 3 or 4 questions. So it's not a whole lot. Pick up the patterns, get the basics down, have the framework. You can then apply that framework consistently to more difficult problems further on down the road.
Leo Gur's at oil rig?
I want to bring that in. As if that's not enough, okay, you will also see some other terms pop up. Oxidizing agent. Now, this is a fun one. What happens to the oxidizing agent? Sometimes it's also referred to as the oxidant. The oxidizing agent was reduced. Why did we call it an oxidizing agent? Because what it is doing is it is acting as an agent to cause something else to be oxidized. Well, if something else is oxidized, what did it have to be? Reduced. They are the swaps of each other. So anytime you see the ing pop into your name, you should slow down and be very careful with your phrasing on it. The other one that you might see, but much less often, is the ant. So if you see the ing or the ants, watch out for those. Okay? Because they are swapping that term or swapping that word on you. Be very, very careful. Questions? No? Okay.
So, does reducing have to do with carbon?
Sorry, say that again.
Well, does reducing have to do with carbon? Because in synonymous reduction means to add carbon.
So let's talk about where these terms come from. It's an interesting idea. Okay. What happened to iodine in the course of this reaction? To go from a +5 to a 0, it gained electrons, which means it was reduced. What happened to its oxidation number? Went from a +5 to 0. What happened to the number? It was reduced. There's where the reduction comes from. It's looking at the oxidation numbers. Where did the term oxidation come from? It's looking at the reactions of oxygen with individual species. So when we look at an oxidation reaction, it is typically increasing the number of oxygen bonds. Okay? Sometimes that's obvious, sometimes it's not. I would argue in this case it's not obvious. Okay? Oh, I lied. Sometimes it is obvious. It is obvious in this case. What happened with our carbon? It went from a +2 to a +4, lost electrons, which meant it was oxidized. Take a look at the carbon. How many bonds or how many oxygens is it bound to in the reactant? How many oxygens is it bound to in the product? 2. Hence it was oxidized. We increased the number of oxygen bonds. That's where oxidation comes from. It is a much larger, broader term than that. It does not always apply to just oxygen bonds. It does apply to other things, but that is kind of an idea on where they're coming from. When you look at other processes, like you said ceramics, adding carbons in, I'm not sure of exactly what that process is, so if you talk to me after class, I can spin that and potentially get that set up. Okay. So, more fun. Identify the oxidation states. Right? And of course, when we're looking at balancing reactions, it's not going to be just looking at the elements. We will also have to balance electrons. The easier way to balance electrons is to balance the charge. What is the charge on the reactant side? +5. What is the charge on the product side? +6. Are our charges balanced? No. Is the reaction balanced? No. So we need to come up with a new way to go through and balance our redox reactions. Okay? I'll show you one method looking at half reactions starting on, not next week, Thursday. Man, sure it can't be next week? On Thursday.